Hi, everybody. Welcome to section 4.1, the exponential functions. At the end of today's lesson, you will be able to define exponential functions, evaluate exponential functions, graph exponential functions, define the natural exponential function, and use exponential functions in applications. So let's go ahead and define an exponential function. A function that can be written in the form of f of x equals some b to the x, where b is greater than 0. Also, b is a number. It's not a variable, it's a number in this situation for exponential functions. And it doesn't not equal 1 is called an exponential function with base b. So that b is our base. The variable is in the exponent, as you can see here. X, our variable, is in the exponent. So some examples of exponential functions are the following. F of x equals 3 to the x. 3 is your base. F of x equals 25 to the x. 25 is your base. F of x equals 2/5 to the x, where 2 over 5 is your base. Notice that's a fraction. F of x equals 5 to the negative x. Notice the variable is negative. F of x equals 4 to the x minus 3 plus 12. Okay, so those are just some examples of exponential functions. Let's go ahead and look at evaluating exponential functions. Evaluating exponential functions is evaluating any other function where you are just substituting in an input for x. You're just substituting in a value for x and getting an output. So for the function for the exponential function f of x equals 3 times 2 to the x minus 4 plus 29, we're going to evaluate at x equals 5. So I'm going to just plug in x equals 5 into this function. So f of 5 equals 3 times 2. I'm plugging in 5. So this would be 5 minus 4 and then plus 29 at the end of the function. So let's go ahead and start evaluating this function. This becomes 3 times 2 to the 1 plus 29. 2 to the 1 is just 2. So this function becomes 3 times 2 plus 29. Remember your PEMDAS multiplication first. This is 3 times 2, so 6 plus 29, and that equals 35. So 35 is 4 of 5. Okay, so that is evaluating exponential functions. Let's go ahead and check out some graphs of exponential functions. So in this case, we have 3 to the x, so it looks something, the function will look like this on the graph. Here's 25 to the x, the function would look like similar. One thing I want to hear is really make sure we could see that tail on the left side. Make sure to put in some arrows too. And here's 2/5 to the x. Notice this function looks a little different than the other ones, than the previous two. This function is now going towards the right side. And likewise, 5 to the negative x has the same feel to it. Okay. One thing we can do here is rewrite this more in the form of our previous examples as 1 over 5 to the x. Because this is a negative exponent, we can move it down. We can move the exponent down to make the exponent positive. And I can also rewrite this as 1/5 to the x. Okay. So what are some things that we notice about these graphs? Some things we notice is that all of the y-intercepts are at 0, comma 1. So what are some things we notice? All y-intercepts at the point 0, comma 1. And another thing that we notice is that none cross the x-axis. None of these cross, and they get very close to the x-axis. They get infinitely close to it as a function goes on forever, but they never cross it. They just get very, very close to the x-axis. So that is a main theme about exponential functions. Okay, let's go ahead and keep observing some more aspects of these functions. So what do you think the domain is for these exponential functions? So recall that domain is x values. Is x values from left to right. Domain is all the x values we are attaining for a function from left to right. So in this domain, we're going off to negative infinity this way. We're going off to negative infinity that way. We're never stopping. Nothing is a barrier for us. So all the x values that we're going to have in any one of these exponential functions is going to be all real numbers. So really, the domain for these exponential functions is just negative infinity to infinity. And now for the range, the range is, if you could recall, y values down to up. So our y values is all, excuse me, the range is all y values we get for a function down to up. So if we look at any which of these graphs, the highest I go is infinity. Nothing is stopping me from going all the way to infinity for each one of these functions. But what's the lowest I can go for each one of these functions? Well, I'm never crossing this x-axis. I'm getting very, very close, but I'm never passing it. So the lowest I can absolutely go is 0. I'm never going to be at 0. I'm going to get very close to 0. So this reason, it'll be a parentheses around 0 and then to infinity. The lowest is 0, the highest is infinity. Okay. And so we can also use a horizontal asymptote to help determine the range, as 0, y equals 0 is a horizontal asymptote. So I'll say horizontal asymptote at y equals 0. One of the other things that we notice about these exponential functions. Okay, so some more background on exponential functions. That exponential function f of x equals b to the x, where b is greater than 1, it is an increasing function. Like examples, or should I say graphs 1 and 2. B3, that's greater than 1, 25, that's greater than 1. So these, an increasing exponential function is graphs 1 and 2. Now, what if we have a base less than 1, b less than 1, and in that case, we have a decreasing function. And this would be in the case of our next two examples. That would be this third graph here where we have 2/5, which is less than 1, and 1/5, which is less than 1, which is the reason why I rewrote the function as such. So these would be decreasing functions. So graphs 3 and 4. Okay. Now let's go ahead and actually plot one of these exponential functions. Let's plot an easy graph using what we previously known. So graph f of x equals 2 to the x. Okay. So let's pick a few x values that will make it easy to calculate. So some easy x values would be -1, 0, and 1. So let's go ahead and figure out what those values might be. So here I have a little table, x, y. I'm picking easy x values, -1, 0, and 1. And my function is f of x equals 2 to the x. Let me move this down a little bit. Okay, so I'm going to plug in -1. So this becomes 2 to the -1. Well, I know that this -1, I can bring down this 2 to make the power positive. So this would be 1 over 2 to the 1, which is just 1/2. So I have the point -1 comma 1/2. Now let's go ahead and check out 0. So 2 to the 0, and anything raised to 0 is just going to be 1. So I have the point 0 comma 1. And now let's go ahead and plug in 1. So 2 to the 1 is just 2. So I have a point 1 comma 2. Okay, so let's go ahead and fill out the rest of these. So this was 1/2, 1, and 2. So let's go ahead and sketch a graph. So what we want to do is get our axes on this scale, give it a nice approximation, get your arrows in each direction and label your axes y and x. So the first point is -1, 1/2. So if we go in the -1 direction, -1, 1/2 would be about right there. Okay, and if we go 0 comma 1, this is 0 and then 1 right here, and then 1 comma 2 be about right there. Okay, so let's go ahead and sketch this graph. So let's go ahead and do 1 point. I want so you could see the general pattern. So what if I want to find -2? So this would be 2 to the -2, which would be 1 over 2 squared, which is 1 over 4. So I would have the point -2 comma 1/4. So here is -2, and then here's about 1/4. So notice how we're just getting closer and closer to that x-axis. We're never touching it. And as our x values get bigger and bigger, we'll just keep getting closer and closer to this axis here, because this number on the bottom will just keep getting bigger and bigger. So this is a quick sketch of this function. Notice how we just chose easy points and we got a general overall sketch. So what would be the domain of this? Like the previous examples, we're still going off in this direction. We're still going off in this positive infinity direction. So our domain would still be negative infinity to infinity. And likewise for our range, we can go all the way to positive infinity Nothing's going to stop us there. But we really can't pass this threshold on the x-axis. So 0 would be that barrier that we can't cross. So our range would still be, as if our previous examples, 0 to infinity. Okay, so this is the graph of y equals 2 to the x. Okay, now let's go ahead and define the natural exponential function. So there's a special base that we would use called the natural base e. And the letter for the base e is this approximate numerical number. Think of it as pi, where pi is approximately 3.14 dot 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 dot. So pi has this symbol for itself, but it has a numerical value. Same thing with base e. It has a symbol e, but it has a numerical value as well. So there's a key on our calculator just above the natural log key for e. There's also a Desmos option. Let me go to that really quickly. So here is Desmos, and the way to find e, you just have to go to this ABC option right here in the bottom left corner. Click that and then click e, and you can see that numerical value right there, 2.718 dot 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 dot. So that's how you would find e in your Desmos calculator if you're using Desmos. If you're using graphing calculator, you can see the e option near that directions. Okay, so let's go ahead and evaluate e. So all we need to do is plug in 2. So what this would become is just e to the 2. And likewise, for f of -3, we're just plugging in -3, e to the -3. So let's go ahead and jump back to Desmos and see what these values might be. So going back to Desmos, e to, make sure to click this option here next to the a squared, a to the b. We wanted to put 2, so that would be 7.389. Likewise, I'm going to do the same thing. Go to ABC, click E, go back, raise it to -3. So you want to click that A to the B option and click -3. And there you go. Those would be how you would calculate our natural base E. Okay, so what we got was approximately 7.389 and approximately 0.0498. So we learned about natural base E. So what do we think the graph of this would look like? So remember, exponential functions are of the form f of x equals b to the x. And if that base b is positive, then increasing, and if that b, sorry, not positive, if b is greater than 1, then it's increasing, and if b is less than 1, then decreasing. Okay, but here our base is e, and e is approximately 2.718 dot 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 dot. So 2.72. So here we are increasing. Let me rewrite that. So f of e to the x, sorry, let me write that. F of x equals e to the x is increasing because at 2.72 dot 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 is greater than 1. So the graph would look much like our other examples where we have an increasing function or increasing exponential function. They all have that intercept at 0, 1, and these functions don't cross the y-axis, and the function would look some as if that. Okay, just one quick thing to note about in the future, that if we have exponential function e to the x, and we want to evaluate at x equals 0, so f of 0 equals e to the 0, e to the 0. So e to the 0 is always going to equal 1. You try it on your calculator, but just a good identity to know off the bat is that e to the 0 just equals 1. It makes life a lot easier. Okay, so that's it for this video for exponential functions. I'll see you next time.